Hi everyone. Today we're doing notes on 6.2 standard units in areas under the standard normal distribution. Suppose Tina and Jack are in two different sections of the same course. Each section is quite large and the scores on the midterm exams of each section follow a normal distribution. In Tina's section, the average mean was 64 and her score was 74. In Jack's section, the mean was 72 and his score was 82. Both Tina and Jack were pleased that their scores were each 10 points above the average of each respective section. However, the fact that each was 10 points above average does not really tell us how each did with respect to the other students in the section. In the figures below, we see the normal distribution of grades for each section. If you notice in Tina's section, there's a smaller standard deviation. And in Jack's section, the scores are more spread out, which means that they had a larger standard deviation. We're going to talk about a z-score or z-value today. This gives the number of standard deviations between the original measurement x and the mean mu of the x distribution. Our equation is z equals x minus mu over sigma. The mean of the original distribution is always 0 in standard units. So we're going to see this formula a lot, so I'm going to write it in words for you. So it's always your value minus the mean divided by the standard deviation. The raw score corresponding to the z-score, this is used to find the original raw score x. Our equation is x is equal to z times sigma plus mu. You can also just plug it into the z-score formula and use algebra to work backwards. So if our x value in the original distribution, if x is equal to mu, then our z value is 0. Our z-score tells us the measurement is near the mean of the distribution. If our x is greater than mu, our z is greater than 0, meaning it's positive, and the measurement is above the mean. If your x is less than mu and your z is less than 0 or negative, and that means the measurement is below the mean. So here's an example. A pizza parlor franchise specifies that the average or mean amount of cheese on a large pizza should be 8 ounces, and the standard deviation only 0.5 ounce. An inspector picks out a large pizza at random in one of the pizza parlors and finds that it was made with 6.9 ounces of cheese. Assume that the amount of cheese on a pizza follows a normal distribution. If the amount of cheese is below the mean by more than 3 standard deviations, the parlor will be in danger of losing its franchise. Okay, so this below the mean by more than 3 standard deviations, what that means is that our z has to be less than -3, right? Because 1 represents 1 standard deviation, so 3 standard deviations represents 3. And we mean below the mean, so that's why it's -3. How many standard deviations from the mean is 6.9? Is the pizza parlor in danger of losing its franchise? So our mu is 8 ounces. Our x is 6.9 ounces. And our sigma is 0.5 ounces. Okay, so z equals x minus mu over sigma. So we have 6.9 minus 8 divided by 0.5, which gives us -2.2. So this tells us that we are 2.2 standard deviations below the mean. Again, because it's negative. So is the pizza parlor in danger? No. It's not more than 3 below. Okay. Rod figures that it can take an average or mean of 17 minutes with a standard deviation of 3 minutes to drive from home, park the car, and walk to an early morning class. One day, it took Rod 21 minutes to get to class. How many standard deviations from the average is that? Is the z value positive or negative, and explain why it should be positive or negative. Please do this one. So we have our mu is 17 minutes, and we have our sigma is 3 minutes. So our x is 21 minutes. Z is equal to value minus the mean over standard deviation. So 21 minus 17 over 3, which gives us 1.33. And this is positive because our value is greater than the mean. So we would say this is 1.33 standard deviations above the mean. Our next question says, what commuting time corresponds to a standard score of z equals negative 2.5? So could Rod count on making it to class in this amount of time or less? So I want you to work backwards and find this one. So again, our formula is z is equal to x minus mu over sigma. So we have negative 2.5 is equal to x minus 17 over 3. So we can multiply these two together. 3 times negative 2.5 is negative 7.5 equals x minus 17. Add our 17 and we get x is 9.5 minutes. So could Rod count on making it to class in this amount of time or less? No, because usually it takes him 17 minutes. Remember, that was our mu. And 2.5 standard deviations below the mean is rare. Okay, so our basic structure of the standard score of the distribution. Again, our z equals the measurement minus the mean over the standard deviation. Our standard normal distribution. This is a normal distribution or normal curve with a mean mu equals 0 and standard deviation sigma is 1. So we have this picture below that you can look at. The standard normal distribution tells us the mean is 0, standard deviation is 1. Any normal distribution can be converted to a standard normal distribution by converting all the measurements to standard z-scores. The area under a standard normal curve, this is why you change the x values to z values. There are lots of tables that show the area under the standard normal curve for intervals along the z-axis. The area is equal to the probability that the measurement of an item randomly falls in this interval. And so again, here we see the empirical rule, 68% of the areas between negative 1 and 1, 95% of the areas between negative 2 and 2, and 99.7% of the areas between negative 3 and 3. All right, so I'm going to show you how to use the table. And so this says, I gave you just a snapshot of the table. It says find the area under the standard normal curve to the left of z equals negative 1. Okay, so again, this is our z value. Here's our mu. And we want to find this area that's shaded blue here. So if I want to find this value, my z value is negative 1. So here I see negative 1. So I'm looking at this yellow highlighted line. And it's negative 1.00, so we're looking at this highlighted pink line, and so this intersection tells us that we have 0.1587 is the area under the curve. So our probability that z is less than or equal to negative 1 is equal to 0.1587. Here's another one. Find the area to the left of z equals 1.18. So again, now here's my mu, here's my z. Now I'm looking for this area. We see that it's to the right of the mean, so we know it should be more than 50% because that 0 is the mean. That would be the 50% mark. So here we're looking at 1.18. So here we have our z is 1.1. Then our hundredths place is 8, so we're looking here. Here's the intersection, 0.8810. So our probability that z is less than or equal to 1.18 is equal to 0.8810. Okay, so there is a way that we can do this in our calculator as well. If we go to the same distribution menu, so we hit second distribution, or the VARS key, it takes you to the distribution menu. We have normal CDF, this is choice 2. And this is what we can use anytime we're using a normal distribution. So the way that you enter these in the calculator is you're always going to do normal CDF, and then you're going to put your lower bound, your upper bound, your mean, and your standard deviation. Okay, again, this stands for lower bound, upper bound, mean, and standard deviation. Okay, so in this case, when we're doing this in the calculator, you would enter normal CDF. Our lower bound, we see this goes to the left forever, right? So I'm just going to pick an arbitrary, really low number. So I'm going to say negative 10,000. That's what I like to choose. Then our upper bound is 1.18. We're going to use the z value. Our mean is 0. Our standard deviation is 1. All right, so let's do a practice here. It says our errors are located in the chart if you would like to use the chart in the back of your book. Otherwise, you can use the normal CDF function in your calculator. So it says, as our z values increase, do the areas to the left of z increase? So the answer to this is yes. So as our z moves to the right, it increases. The area to the left will also increase. If a z value is negative, is the area to the left of z less than 0.5? The answer to this is also yes, right? Because if we're looking at our standard normal curve, again, here is our 0 point. And so we have half of our data or our probabilities on the left, half on the right, because the total is going to add up to 1. Here's our negative z values. Here's our positive z values. So if our z is negative, the area to the left will have to be less than 0.5 or less than half. All right, if a z value is positive, is the area to the right, is the area to the left of z greater than 0.5? And this answer is yes as well, because if we're in that positive range, we know we have more than half, so it will be greater than 0.5. So here's a summary of how you use the table. So areas to the left of a specified z value, we use the table entry directly. So here's our z value, and again, it represents this area to the left, so we use it directly. Areas to the right of a specified z value, you look up the table entry for z and subtract the area from 1. So if we're looking for this to the right, we take the entire curve, 1 minus the area to the left. And this is similar to what we did with the binomial, geometric, and Poisson distributions, where anytime we wanted greater than or equal to a value, we did 1 minus the less than or equal to. So you can think about this in the same way. Areas between two z values, z1 and z2, we subtract the table area for z1 from the table area of z2. So again, if I want the values between these two, we take our z2, our higher z value, minus our z1, which is our lower z value. Okay, so find the area between z equals 1 and z equals 2.7. First, sketch a diagram showing the area. So if I sketch a picture, remember the middle is always 0. So here is Z is 1, and we'd say this is about 2. So here is our 2.7 is about here. So we're looking for this shaded area between 1 and 2.7. So we want the probability that our Z value is between 1 and 2.7. So we're going to do the probability that Z is less than or equal to 2.7 minus the probability that Z is less than or equal to 1. So if we look these up in the chart, for 2.7 we get 0.9965, minus for 1 we get 0.8413. When we subtract these, we get 0.1552. Now, remember, we can also do this in the calculator. And just a reminder, in your calculator, for normal CDF, if you're using z-scores, then your mean is always 0 and your standard deviation is always 1. Okay, so keep that in mind. So if we want to do this one in the calculator, we could do normal CDF. And because we're going between these two values, our lower bound is 1, our upper bound is 2.7, our mean is 0, and our standard deviation is 1. And then we will get that same answer, 0.1552. Here's our next one. Find the area to the right of Z equals 0.94. First, sketch a diagram. So again, let's sketch a standard normal curve. Here's our 0. And here's about Z is 0.94. We want the area to the right. So that's all this. So we want the probability that our Z is greater than or equal to 0.94. So that will be 1 minus the probability that Z is less than 0.94. If using the chart, we can look up 0.94 and we get 0.8264. Subtract that from 1 and we get 0.1736. If we wanted to do this in the calculator, we could do normal CDF. And our lower bound in this case is going to be 0.94 because we want the area to the right. So then we need to pick a large number for our upper bound. I'm going to choose 10,000 because I like using 10,000 and negative 10,000. Our mean is 0 and our standard deviation is 1. And we end up getting the exact same result. Okay. The probability that Z is greater than or equal to 1.15 refers to the probability that Z values lie to the right of 1.15. Shade the corresponding area under the standard normal curve and find the probability that Z is greater than or equal to 1.15. Please do this one. Okay, so first let's draw our curve. Here's our 0. Here's about where 1 is at. So we want 1.15. And we want the area to the right. This is similar to the one we just did. Probability Z is greater than or equal to 1.15. That's equal to 1 minus the probability that Z is less than 1.15. If we use our chart, that's going to give us 1 minus 0.8749, which leaves us with 0.1251. If you did this in the calculator, we could also do normal CDF. Our lower bound is 1.15. Our upper bound, we can choose 10,000. Mean is 0. Standard deviation is 1. And we will get the same result. All right, now I would like you to find the probability that z is between negative 1.78 and 0.35. Sketch the curve and find the probability. All right, so here's our 0. This is about -1 and +1. Here's -2, +2 about. So we got negative 1.78, so we're about here. And positive 0.35, so it's about here. So we're finding this area under the curve for the probability. So we have the probability, negative 1.78 less than or equal to z, less than or equal to 0.35. So I can do the probability that z is less than 0.35 minus the probability that z is less than negative 1.78 if we're using the chart. So these values are 0.6368 minus 0.0375, and this gives us 0.5993. If you did this using the calculator, we can do normal CDF. Our lower bound is negative 1.78. Upper bound is 0.35. Mean is 0. Standard deviation's 1. And we end up with the same result. And that's all I have for you for today.